Welcome to the video on RC oscillators. So there are two different types of RC oscillators. The first one is RC phase shift oscillator. Next one main bridge oscillator. Now what is the comparison between RC oscillator and LC oscillator? Okay, in RC oscillator there is resistor and capacitor component. For LC oscillator there is a inductor and capacitor component. So basically RC oscillators are called as low frequency oscillator. LC are called as high frequency oscillators. Okay, so this RC oscillators need high power supply and it is very difficult to maintain the sustain of oscillations, but for LC there is little bit power supply is needed. That is the main difference between RC and LC oscillators. So let us see the first type of RC oscillator. The first type is called as RC phase shift oscillator. So first of all, what is meant by phase shift? Okay, so the phase shift oscillator is nothing but as a low frequency oscillator. The first one is it's a low frequency oscillator, and in this RC phase shift oscillator, uh, for maintaining the sustain of oscillations, we need 360-degree of phase shift. So at first of all, the amplifier which produces 180-degree phase shift and the feedback network provides again 180-degree phase shift. So the total phase shift can be given as 360-degree. Now you can see the 180-degree phase shift in the feedback signal can be achieved by suitable RC network consists of three RC sections. Okay, so now you are seeing the single RC section. So here a capacitor and resistance, the single RC section which produces 60-degree phase shift. Okay, so at the same time here in this diagram three RC sections are there. So one section, two section and three sections. So combinedly these three sections produces 180-degree phase shift. So let us see the circuit diagram. Yes, this is the circuit diagram for RC phase shift oscillator. Here, this is your common emitter configuration, and this is called as feedback network. So, this configuration which produces 180-degree phase shift, and this feedback network produces again 180-degree phase shift. So, the total is called as 360-degree phase shift. So, let us see the circuit arrangement. Yes, the phase shift oscillator with CE configuration is shown in the figure. So the resistance R1 and R2 provides the DC emitted bias, and RE emitter resistance and CE emitter capacitor provides the temperature stability and prevents the AC signal degeneration. So this circuit which contains three RC sections, the number one RC section, second RC section and third RC section. So here this is the oscillator, so we should give the positive feedback. And let us see the working principle of RC phase shift oscillator. I already explained. So the RC network produces the phase shift of 180-degree, and the amplifier, common emitter amplifier, produces phase of 180-degree. And yes, these kind of oscillators are used for audio frequencies. And since the LC circuit look bulky and expensive, so RC oscillator preferred for low frequency applications. And now I'm going to replace this circuit diagram into a equivalent circuit diagram. Yes, this is the equivalent circuit diagram. So in this diagram we should replace some important components. So we should replace the current source by the voltage source, and we need to analyze the feedback network so we can draw the equivalent circuit for the feedback network alone. So here we should going to discuss about the equivalent circuit of the feedback network. Yes, and this is the equivalent circuit. Here we should replace the current by voltage source, and this HFE IB into RC is not a voltage source actually. It should represents the voltage drop across the transistor. Here the HFE IB is the current component and this RC is the resistance component, and this C and R is your first RC section, and the current can be given as I1, and this R is your second RC section. The current can be given as I2, and the third, this C and R can be given as third RC section. The current should be I3. So this is a very important circuit diagram. In this circuit diagram we are going to find out the three currents I1, I2 and I3. Yes, now I am going to apply KVL in the loop 1. This is called as loop 1. The current in the loop 1 can be given as I1. So I am going to apply KVL in the loop 1. So after applying KVL, I can get this equation HFE IB into RC. Yes, and plus I1 into RC, yes, and plus I1 into this C. So C can be written as J by, sorry, 1 by J omega C, and this R. So this R is nothing but as resistance R into I1 minus I2, because the two currents can be passed in this resistance I1 and I2. That is what I1 minus I2 into R equal to 0. So this is the first equation. Here I am going to modify this equation. I am going to separate the terms of I1, I2 and I3. So after simplifying this expression, I can get the equation as RC plus R plus 1 by J omega C into I1 minus I2 R plus HFE into I3 RC equal to 0. So this is for the first equation. And next I am going to apply KVL in the second loop. So in this loop I am going to apply the KVL. So here this R is common for this loop and this loop. No, now I2 minus I1 into R, I2 minus I1 into R plus I2 into 1 by J omega C. Okay, and here this R is common for this second loop and third loop. Now I2 minus I3 into R. So I2 minus I3 into R. So after simplifying this expression, I can get the second equation minus I1R plus 2R plus 1 by J omega C into I2 minus I3R equal to 0. So this is the second equation. And now I am going to apply the KVL in this third loop. So in the third loop, we can get the equation as here this R is common for I2 and I3. Now I3 minus I2 into R plus I3 into 1 by J omega C plus I3 into R. So this is for the third equation. So after simplifying this equation, I can get the third equation as minus I2R plus 2R plus 1 by J omega C into I3 equal to 0. There is no I1 component in the third equation. So by using the three equation, we are going to form the determinant with the coefficient of I1, I2 and I3 in the matrix format. Okay, we already know how to write the matrix format I1, I2 and I3. So this is plus, minus, plus, minus, plus, minus, plus, minus, plus, and these are the corresponding values of I1, I2 and I3. Now I am going to find out the determinant. Okay, in this equation I am going to find the determinant. So we already know about that. So RC plus 1 by J omega C plus R. So this model. So 2R plus 1 by J omega C into 2R plus 1 by J omega C and minus R square. So that is for this first equation. And for this next, for this R, already minus will be there. This minus into minus plus, plus R into this one. Okay. So 0 into minus R is 0, but minus R into 2R plus 1 by J omega C. That is what here. And the third one, yeah, this one. So this term will be 0, but this is what R square. Okay. So HFE RC into R square equal to 0. So is again the same simplification. So please do the simplification very carefully, because if any term will be missed means the whole concept will be wrong. So please take care and carefully solve the simplification. After simplification, we can get this equation. So is RC plus R into 3R square minus 1 by omega square C square plus 4R by J omega C plus 1 by J omega C into 3R square minus 1 by omega square C square plus 4R by J omega C minus 2R cube minus R square by J omega C plus HFE RC into R square equal to 0. This is the important term. In this term, we are going to separate the real and imaginary term. Okay, we are going to separate the real and imaginary terms. Yeah, this is the equation. Yes, this is the equation. After we can apply the formula 1 by J equal to minus J. After applying this value in this equation, we can get the equation as this one. Okay, so RC plus R into 3R square minus 1 by omega square C square minus J of RC plus R. So this is the imaginary term, and this one is also imaginary term, and this is also a imaginary term. Okay, so to find the frequency of oscillation, we should equate the imaginary part should be 0. Okay, so this is what the imaginary part should be 0. So now I am going to take, yes, yeah, now I am going to take 1 by omega C as common, and this is the value equal to 0. So the omega C goes to that side, right hand side, it will be also 0. So after simplification, we can get the equation as 1 by omega square C square equal to 6 R square plus 4 R into RC. So in some textbooks, the R is the value of RC by R can be given as K. Okay. So 1 by omega square C square equal to 6 R square plus 4 R into RC. So after simplification, omega square equal to 1 by c square into 6r square plus 4r into rc, taking r square outside. After that, you can get the equation as omega equal to 1 by rc root of 6 plus 4 rc into r. Sometimes the value of rc by r equal to k. Okay, k is your constant value. So omega equal to 2 pi f. So 2 pi f equal to this equation. Then notice f equal to 1 by 2 pi rc into 1 by r 6 plus 4 rc into r. So this is what the frequency of oscillations in frequency of oscillation of RC phase shift oscillator. Now you can find out the condition of oscillation. So for finding the condition of oscillation, we should equate the real terms should be 0. So and these are the real terms of RC phase shift oscillator. Again, we should do the simplification. We should do the simplification. We can get this equation, and at one stage we can substitute the value RC equal to R. So where is the value of RC? We can substitute the value RC equal to R, and finally we can get the equation as HFE R cube equal to 56 R cube, and R cube will be cancelled. So the HFE, the forward current gain, should be given as 56. Okay, this is also very important. And the advantages of RC phase shift oscillators is it's a very simple circuit to design, and it is only used for audio frequency range, and there is a fixed frequency oscillator. And the drawbacks of RC phase shift oscillators are the frequency stability is very poor due to the effect of temperature, and also it is fixed frequency oscillator, but the resistance and capacitance of all sections have to be changed to satisfy the oscillating condition, but it is practically impossible. But anyway, these two are the main drawbacks of the RC phase shift oscillator. Okay, so again I'm repeating. So especially this RC phase shift oscillator have some complex derivation. It's not a complex derivation, it's a very simple derivation, but we have to solve the derivation very carefully. So the very important for finding the frequency of oscillation, we should equate the imaginary part should be 0. So that is what this f. So f equal to 1 by 2 pi rc into 1 by root of 6 plus 4 rc by r. It's a very important formula for solving the 2-mark problems or 13-mark problem questions. Thank you.